This lesson will discuss the regulatory and operational requirements for ETOPS. ETOPS stands for Extended Range Operation with Two-Engine Airplanes. Normally, a two-engine airplane must stay within 60 minutes flying time of an adequate alternate. This rule restricts the area of operation and may result in increased route distance and fuel. For instance, consider a New York to Madrid flight under the 60-minute rule. However, if an operator meets ETOPS requirement, he may fly in areas that are 120 or even 180 minutes from a suitable alternate. ETOPS operation increases the routes available to economical two-engine airplanes. ETOPS operation requires two levels of regulatory approval. First, the airplane manufacturer must obtain a type design approval for the engine-airframe combination. Then, the airline must obtain operational approval from their regulatory authority. Type design approval is based on engine reliability, system design and reliability, and a validation test flight. Engine reliability is measured by in-flight shutdown rate. For an engine to qualify for 120 minutes ETOPS, most regulatory agencies require less than 5 shutdowns per 100,000 hours of operation fleet-wide. For 180 minutes ETOPS, the typical requirement is less than 2 in-flight shutdowns per 100,000 hours of operation. The airplane may require additional equipment to meet the system design and reliability standards for ETOPS. The APU is normally upgraded to improve reliability and improve in-flight starting performance. On some models, a hydraulic motor generator has been added to increase dispatch flexibility for ETOPS. If required, the HMG provides an additional source of AC electrical power. The highlighted flight deck equipment is available with the HMG as the only source of electrical power. Electronic equipment cooling systems have been upgraded. Cargo fire suppression time must be increased to meet ETOPS requirements. The final step in obtaining type design approval involves a manufacturer's validation test flight. This test flight verifies the airplane's flying qualities and the flight crew workload with various systems inoperative. This test flight also is used to verify the airplane's ETOPS-related performance. To obtain operational approval, the airline must show that they have operational and maintenance programs that address ETOPS requirements. This includes additional training for flight crews and maintenance personnel. The airline ETOPS operations program must include route planning, dispatch considerations, and an operations specification. An operational validation flight may also be required. An airline ETOPS maintenance program must include the identification of ETOPS-related tasks, ETOPS parts control program, monitoring of the airline's in-flight shutdown rate, an oil consumption monitoring program, and an engine condition monitoring program. This program will identify engine anomalies before they become a problem. This will also reduce the possibility of a problem during a prolonged single-engine diversion. An important item in an ETOPS maintenance program is the similar task concept. If a similar task has been done on 2 separate but similar ETOPS critical components and a satisfactory ground test does not exist, a maintenance verification flight may be required. This verification flight is to ensure that the problem has been resolved and that identical maintenance errors have not been introduced to both components. Examples of this are the improper installation of O-rings on a chip detector in both of the engines during routine maintenance or the removal and replacement of both the left and right engine fuel control modules. The required verification flight may be performed during a non-ETOPS portion of a scheduled revenue flight. The first step in ETOPS planning is to define the route. Let us consider a route from New York to Madrid. For the purpose of this lesson, we will assume a great circle routing is desired. Our next step is to identify the adequate en route alternate airports along this route. An adequate airport is one that meets certification standards, meets the airplane's performance requirements, and has adequate ATC, communications, navigation aids, and firefighting equipment. For an adequate airport to be used as an ETOPS alternate, it must meet the requirements of a suitable airport. A suitable airport is an adequate airport with forecast weather conditions above ETOPS minimums. The ETOPS weather minimum is a function of the landing aids available at the alternate. For a non-precision approach or a single precision approach airport, the ETOPS minimum is an additional 400-foot ceiling and an additional 1-mile visibility above the lowest authorized minimum for the airport, or the other listed requirement, whichever is more restrictive. For an alternate with 2 or more separate precision approach-equipped runways, the ETOPS requirement is an additional 200-foot ceiling and 1/2-mile visibility above the airport's minimums, or a ceiling of 400 feet with 1-mile visibility. Now that the adequate airports have been identified, we can draw circles centered on these alternates to determine the allowable area of operation. The radius of each circle is a function of the chosen engine inoperative diversion speed and the maximum diversion time. This radius is also called the diversion distance. The diversion distance is the distance traveled in the diversion time at the diversion speed following an en route engine failure. The diversion distance is computed for a standard day in still air. The distance will be greater if a larger diversion time is chosen and/or a higher one-engine inoperative diversion speed is used. A diversion distance chart is applied in Chapter 2 of the Flight Planning and Performance Manual. The chart is used to determine the circle radius and therefore the allowable area of operation. We will look at the 60-minute circles as well as 120-minute and 180-minute circles. With 60-minute circles, a non-ETOPS operation, the routing cannot be direct. With 120-minute circles, a direct routing can be scheduled. As you can see, 120-minute ETOPS approval provides economic and operational benefits. Now consider the possibility of an alternate being closed. In this case, the displayed route would be required to meet the 120-minute ETOPS rules. If 180-minute ETOPS has been approved for the airline, a direct route would again be available. Now let us consider the dispatch requirements for ETOPS. Each airline's MEL must specifically identify ETOPS items. The FAA Master MEL identifies ETOPS constraints by using the abbreviation ER. For example, Item 24-00-2 of the Master MEL lists ETOPS dispatch requirements for an inoperative APU-driven generator. Not all the MEL items are this obvious. Consider the air-driven pump. This item may be inoperative, provided the HMG is not required. The HMG is required for ETOPS only if one of the other 3 sources of AC power is inoperative. Therefore, if one of the engine generators or the APU generator is inoperative, the HMG is required for ETOPS. If the HMG is required for dispatch, the air-driven pump may not be inoperative. Your airline is responsible for identifying all the possible ETOPS dispatch requirements in your own MEL. The ETOPS entry point is the point on the outbound route, which is 1 hour flying time at the approved one-engine inoperative cruise speed from an adequate airport. For our flight, this occurs at the highlighted point. The entry point is sometimes included on the computerized flight plans. The flight plan should also identify the ETOPS critical points. A critical point, CP, is the point on the intended route where the diversion time from the two closest ETOPS alternates is equal. This is sometimes referred to as an equal time point, ETP. The critical point location is typically listed on the flight plan by latitude and longitude or distance from a waypoint along the intended track. These critical points can be entered into the FMC as additional waypoints to assist in position monitoring. To legally dispatch an ETOPS flight, the weather at the planned ETOPS alternates must meet the requirements for a suitable airport from 1 hour prior to the earliest possible arrival time until 1 hour after the latest possible arrival time. The earliest possible arrival time assumes the diversion occurs at the first critical point for the airport. The latest possible arrival time assumes diversion from the second critical point for the ETOPS alternate. The flight plan should list the ETOPS suitable alternates. The final ETOPS dispatch requirement is the critical fuel scenario. The critical fuel scenario ensures that in the event of a diversion, there will be adequate fuel available to fly to the en route alternate airport. The critical fuel scenario assumes a pressurization failure at the critical point, followed by an emergency descent to 10,000 feet and a subsequent cruise to the nearest en route alternate. At the alternate, descend to 1,500 feet, hold for 15 minutes, missed approach, then approach and land. The critical fuel scenario includes a 5% allowance for errors in the forecast winds and an increment for APU fuel burn. The critical fuel scenario fuel calculation must take into account the predicted weather conditions, such as hotter than standard temperatures and possible icing conditions. The calculated critical fuel must be increased to account for any performance deterioration. If the airline does not track deterioration, a 5% allowance must be used. The critical fuel scenario must be checked for both all engines operating and with one engine inoperative. The larger fuel requirement must be used. The all-engine critical fuel requirement is calculated at long-range cruise speed at 10,000 feet. The one-engine inoperative critical fuel requirement is calculated at the chosen ETOPS speed at 10,000 feet. If the critical fuel required at a critical point is greater than the scheduled fuel on board, the required fuel load must be increased. Two other criteria for ETOPS operational approval are an operational validation flight and an operation specification. An operational validation flight may be required to demonstrate the airline's capability to safely conduct and support the intended ETOPS operation. The airline's operations specification needs to be modified to document the limitations and standard operating procedures to be used for ETOPS. The OpSpec normally would include registration number of the ETOPS-equipped airplanes, the allowable area of operation, any altitude restrictions, the chosen diversion time and speeds, authorized alternates, as well as any other pertinent information. Although there are no unique flight crew procedures required during an ETOPS flight, the flight crew responsibility for monitoring the airplane's position, fuel, and system status takes on increased importance. The flight crew must also check the weather status at the ETOPS alternates as the flight progresses. As with any other flight, if an event does occur, the flight crew must make a decision on whether to proceed, divert, or turn back. The ETOPS rules ensure that the flight crew has the resources to make the best decisions when faced with an in-flight event. The flight crew is not bound by the ETOPS rules for any specific course of action. They must evaluate the situation and take the action dictated by the actual circumstances. In the event of an ETOPS diversion due to an engine failure, the flight crew must determine the best speed, altitude, and thrust rating for the single-engine flight to the alternate. The flight crew is expected to fly the ETOPS diversion speed, but if in the judgment of the flight crew it is better to fly a different speed, then they may deviate and fly the best speed based on the circumstances. If time is the greatest concern, the decision might be to fly at maximum continuous thrust at the highest altitude possible. If time is not the greatest concern, the decision might be to fly at maximum cruise thrust, resulting in a longer diversion time and a lower cruise altitude. The FMC engine-out drift-down speed cannot be modified by the flight crew. Therefore, the engine-out altitude capability at the ETOPS diversion speed is usually not available from the FMC. To obtain this information, the flight crew must refer to Chapter 3 of the Flight Planning and Performance Manual. This chapter contains information to support ETOPS en route operations. An ETOPS operator must have performance data in their operational documents, which addresses the possibility of flying a significant amount of time on one engine at the chosen diversion speed. To meet this requirement, the Boeing Flight Planning and Performance Manual contains charts that allow the calculation of engine-out altitude capability and diversion fuel. There are altitude capability tables for both maximum continuous thrust and maximum cruise thrust at the different ETOPS speeds. These tables reflect the airplane's performance capability and contain no conservatisms. Note that the altitude correction for anti-ice bleed is significant. This should be taken into account when deciding on a course of action. The Flight Planning and Performance Manual also provides one-engine inoperative in-flight diversion charts. These charts allow the quick calculation of diversion fuel for different cruise altitudes. The critical fuel scenario check in the flight plan assures that fuel should not be a concern if the diversion is flown at the chosen ETOPS diversion speed or below, and the diversion is to one of the closest ETOPS alternates listed in the flight plan. Chapter 3 of the Flight Planning and Performance Manual also provides one-engine inoperative cruise tabulation information for a range of ETOPS diversion speeds. In this lesson, you were shown that the ETOPS approval process can be quite involved for both the airplane manufacturer and the operator. This approval process, along with the dispatch planning, ensures that the flight crew will have the resources to safely conduct a flight in an area 2 or even 3 hours flying time from an airport. The actual flight crew ETOPS work is relegated to checking and decision-making. By the time the flight crew is assigned to fly an ETOPS route, the airline's engineers have determined the required ETOPS diversion time and chosen the ETOPS speed. The area of operation is known. By the time the pilot arrives at dispatch, the ETOPS flight plan has been created. The flight plan should list the ETOPS critical points and the ETOPS en route alternates. The fuel load will have been checked against the critical fuel scenario. The flight crew will then check the flight plan and ensure the scheduled route is within the area of operation for the listed en route ETOPS alternate airports. The dispatchers may have already checked the forecast weather at the ETOPS alternates and check the company MEL for ETOPS considerations. If not, the flight crew will need to do these tasks. The pilot will also need to check NOTAMs at the en route ETOPS alternates. If the forecast weather does not meet the suitability requirements, the flight crew must demand a new flight plan with different alternates or a new routing. During the flight, the crew needs to monitor airplane position, fuel status, and system status, along with the weather, at the en route alternates. The flight crew may be asked to record engine data to support the engine condition monitoring program. The final job the crew has is the most important. In the event of an en route event, the crew will have to decide whether to continue, divert, or turn back. This decision has to be based on the circumstances at the time of the event. If a diversion occurs because of an engine failure, the flight crew must decide at what speed and thrust rating to fly the engine inoperative diversion. Enjoy the layover at the exotic destination to which your ETOPS flight takes you.